Hello. Good afternoon, everyone. In last lecture, we have seen one example that was given for you for solving. And before that, we have seen the concept of capacitance, right? So, in capacitance, how actually the formula is derived for only the capacitance. And we have seen the two types of capacitors. That is, one is the parallel plate capacitor, and second is a circular. Okay, circular capacitor we have seen, or it is also called the spherical capacitor. Okay, so there are two rings of that capacitor having radius a and b. For that, formula is different, and when you are considering a simple parallel plate capacitor, for that also your formula is different, right? So yesterday I given you one example, so all of you solve that, at least try to solve that example. Yes or no? Because that example was on the simple formula of the parallel plate capacitor only. Okay, we'll see that example now. So here the example is this one, and yesterday only I explained this figure also. So epsilon r1, epsilon r2, and epsilon r3. Only epsilon r1 and r2 are given. That is the relative permittivities. Okay, for region 1, for region 2, and for region 3 it is not given. And the distance of all three regions is given. So distance d1 is from 0 to 1, that is 1 mm. Then distance d2 is from 1 to 3, that is total distance is d2 is 2 mm. And distance from 3 to 5, okay, third layer, means it is total d3 is equal to 2 mm. Okay, so this is a parallel plate capacitor, and we have to calculate the capacitance per meter square area. We have to find capacitance C per meter square area, means C upon A. We have to find if this epsilon R3 is that for air. Okay, means we have to find this when epsilon R3 is that for air. Then just tell me, what is epsilon R3 for the air? What is the value of relative permittivity for air? Yes. What is value of relative permittivity for air? Okay, so it is equal to 1 for air. Remember, for air, it is equal to 1. Okay, now for parallel plate capacitor, formula is C is equal to epsilon 0 epsilon R into A divided by D, right? So we have to find here the capacitance per meter square area. So this A is taken to the left side. So this C upon A is equal to epsilon 0 epsilon R divided by D. Now we have to apply this formula for all three layers. Okay, so first we'll find for this first region, that is where this distance is equal to d1, and this d1 is equal to 1 mm. Okay, so this c1 divided by a1 is equal to epsilon 0 epsilon r1 divided by d1. Now epsilon r1 is given, it is equal to 2.5. Epsilon 0, we know this constant as 8.854 into 10 raised to minus 12, divided by distance d1. Now d1 is equal to 1 mm, right? 1 mm. So 1 mm is 1 into 10 raised to minus 3. So if you solve this, you're getting this C1 upon A1 is equal to 22.135 into 10 raised to minus 9 farad per meter square, because this is not only the capacitance, it is the capacitance per meter square area. Okay, so the unit is farad per meter square. Then we have to find for the second region, that is C2 divided by A2 is equal to epsilon 0 epsilon R2 divided by D2 is equal to, now epsilon R2 this epsilon R2 is equal to 4. Epsilon R2 is equal to 4. And the distance D2, here you can see the distance D2 is equal to 2 here. Okay, 2. So, therefore, this C2 divided by A2 is equal to epsilon 0, same value, constant, then epsilon R2, that is 4, and the distance D2 is 2 mm. So, it is 2 into 10 raised to minus 3. Okay, so this C2 divided by A2, we are getting as 17.708 into 10 raised to minus 9. And the unit is farad per meter square. Okay, and same for we have to find for the C. Hello. So now for C3 upon A3, it is epsilon 0 epsilon R3 divided by D3. Now here what condition is given? Actually the value of epsilon R3 is not given, but we have to consider that epsilon R3 is that for the air, and this relative permittivity for air is equal to 1. Okay, for air is equal to 1. So therefore this epsilon 0 into epsilon R3 is equal to 1 divided by D3. Now D3 is also 2 mm. So it is 2 into 10 raised to minus 3. Okay. So this C3 upon A3 is equal to 4.427 into 10 raised to minus 9 farad per meter square. Okay. Now we find all the C3 upon A3. Now we know the formula. We have to find out the equivalent, right? So we know the total capacitance. To find the equivalent capacitance, formula is 1 upon C is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, right? Resistances we are adding when these are connected in series, we can simply add them. Okay, but here for capacitance, when the capacitances are connected in series, their addition is done in this way. So we have to find now not only the capacitance, but we have to find here the capacitance per unit area, right? So it is 1 divided by C divided by A. So for all, it is A upon C is equal to A1 upon C1 plus A2 upon C2 plus A3 upon C3. Okay, so just take the reverse, means 1 divided by 22.135 into 10 raised to minus 9 plus this one, that is A2 divided by C2, and this is A3 divided by C3. Okay, just okay. So now C3 upon A3 is equal to 4.427 into 10 raised to minus 9 farad per meter square. So just uh, take it into the denominator and you will get the A3 upon C3. Okay. So just solve this. After solving, you'll get 1 upon C upon A, which is equal to A upon C, and it is equal to 0.326 into 10 raised to 9. And the unit will also change here. The unit is meter square per farad. Okay. Remember, when you are changing this, you have to change the unit also. Therefore, this C divided by A is equal to 1 divided by 0.326 into 10 raised to into 10 raised to plus 9. Okay, so it is A upon C. Now again, if you take the inverse, you are getting this, which is equal to 3.067 into 10 raised to minus 9 farad per meter square. Here you are getting the capacitance per unit area. Okay. So in 10 raised to minus 9 means it is picofarad. It is directly written. Now the second condition B is given. So the question is, we have to consider this epsilon R3 is equal to epsilon R1, and epsilon R1 is equal to 2.5. Now for this we have to find here. So considering epsilon R3 is equal to epsilon R1, which is equal to 2.5, only your third term will change, that is C3 upon A3 is equal to epsilon 0 epsilon R3 divided by D3. Now epsilon 0 is constant, epsilon R3 is 2.5, and D3 means distance for the third layer is 2 into 2 mm, means it is 2 into 10 raised to minus 3. Okay, so C3 upon A3 is equal to 11.067 into 10 raised to minus 9 farad per meter square you are getting. Again, you have to take in the denominator. Okay, so it is 1 divided by C upon A. You are getting means A upon C. Okay. For this, again, you have to add all the three equations. That is, so for epsilon R1, this is for epsilon R2, and this is for epsilon R3. Okay, so if you solve this, you are getting the equivalent as A upon C is equal to 0.1918 into 10 raised to plus 9. Again, take the inverse so that you will get the capacitance, the total capacitance per unit area, and it is equal to 5.214 into 10 raised to minus 9 farad per meter square. Okay, so all of you understood this? How you are taking this? How to take? If this is given, you just remember this formula. For every layer, you have to find this epsilon R and D, which is already given. Then C upon A, find this. To find equivalence, you know the formula 1 upon C is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3 here. But what is asked? It is C upon A is asked, right? So write this and solve according to the questions asked. Okay. Now the next point is, समजलंय का हे? Yes or no? Hello? समजलंय का? Roll number 9, Mohini. Okay. Now, next point is energy stored in capacitor, right? So we know that the capacitors and inductors are storing energy, right? So your capacitor stores energy in terms of voltage, and your inductor stores energy in terms of current, right? So these two are the energy storing devices. So we are finding now the energy stored in a capacitor. Okay, so for this, we are considering one parallel plate capacitor here. Consider one parallel plate capacitor. The upper plate is positively charged and the lower plate is negatively charged, right? So, and across this, we are connecting a supply V. Now, the distance between these two plates is D, and in between these two plates, there is a dielectric material. Okay. Now, we know that the capacitor is used to store energy. Now here it is a parallel plate capacitor which is supplied with potential V. Now here let A bar N is the direction normal to the plates. Okay, is a direction normal to the plates, and E bar is equal to V upon D A bar N. Okay, so energy stored is given as here E bar, which is equal to V upon D, means the supply voltage divided by the distance into the perpendicular unit vector to that parallel plates is normal unit vector, that is A bar N. So E bar is equal to V upon D into unit vector A bar N. And we have also seen the formula for energy stored, right? Energy stored in second chapter we have seen energy density, right? Energy stored. So that energy stored is given by it is WE is equal to 1 divided by 2 into volume integral of D bar dot E bar into dv. This is the formula which we have already derived. Okay, so it is equal to, now we are writing this d bar in terms of e bar. Okay, we know the relation between d bar and e bar. This d bar is equal to epsilon e bar. Okay, d bar is equal to epsilon e bar. So we are, instead of this d bar, we are writing epsilon e bar. So it is equal to 1 divided by 2 volume integral of epsilon into e bar instead of d bar dot this e bar into dv. Okay, now we are taking the dot product of this e bar dot e bar. Now e bar dot e bar is equal to mod of e square, right? Because any vector is equal to, if we are considering vector, that vector is equal to its magnitude into direction. So the direction is same, and their dot product is equal to 1. Therefore, e bar dot e bar is equal to mod of e square, or you can write it as only e square. Okay, so it is equal to 1 divided by 2 volume integral of epsilon into mod of e square into dv. Mod of e square into dv. Now, but here mod of v bar is equal to v upon d. Mod of e bar. Okay, so this is e bar is equal to v upon d into a bar n. Now, if you take its magnitude, if we take its magnitude, then your unit vector get cancelled there, and there will be only the magnitude, that is v divided by d. Okay, therefore this we is equal to 1 divided by 2 into volume integral of this is equal to 1 divided by 2 volume integral of this epsilon. And what is this mod of e bar? Is v divided by d. So it is mod of epsilon e square. So we are doing this as a square. So it is v square divided by d square into dv. So it is equal to 1 divided by 2 epsilon constant, v square upon d square constant, and for volume integral into dv. Now volume integral of dv we have to take here. Now for this parallel plate capacitor, the total volume taken is, so what is the total volume? Means total volume, what we are considering when we are considering a rectangle, for that dv is equal to that differential volume is the multiplication of your all differential lengths. Now what are here the lengths? Here we are considering total area and the gap, right? Total height, that is that distance d. Therefore the volume is equal to a into d. The total volume is a into d. So we is equal to 1 divided by 2 epsilon v square into, instead of dv we are writing here a into d divided by d square. So it is equal to 1 upon 2 epsilon. I'm just writing this like epsilon into a and v square divided by d. Okay, v square divided by d, because this 1 d and d get cancelled, only d is remaining in the denominator. Okay, so we is equal to 1 upon 2 epsilon into v square. Okay, d and d1d get cancelled, so it is v square divided by d. Okay, and it is this a is only taken here. Now this term epsilon a into d is what? Yes, epsilon a into d is equal to what? Yes, anyone? What is this epsilon a into d? Swarsha? What is this epsilon a into d? Prajakta? Yes, anyone? So who is present in lecture? Swapnali, what is this C in epsilon into A divided by D? So it is equal to capacitance C. Okay, we have seen the equation for parallel plate capacitor. C is equal to epsilon 0 epsilon R into A divided by D. Okay, so it is nothing but epsilon divided by D. So WE is equal to 1 upon 2 into this term as C into V square, and this energy is measured in joules. Okay, so remember this equation is asked in examination. Okay, so WE is equal to 1 upon 2 CV square in joules. Okay, now the next point is energy density. So energy density is the energy stored per unit volume as volume tends to 0. Okay, so here WE equation we are having WE is equal to 1 upon 2 epsilon volume integral of mod of E square into dV. Now here WE is equal to 1 upon 2 epsilon mod of E square. It is the energy density when you are taking the volume as a 0. Okay, means when your volume will tend to 0, that equation is considered as energy density. So you have to remember this equation only. For energy density, the unit is joule per meter cube. Okay. Then after that, you can relate this or do not. Okay. This is dependent on you only. But the final equation is WE is equal to 1 upon 2 epsilon E square. Okay. And in joule per meter cube. So if you want to write it in terms of D bar, you can use the relation as D bar is equal to epsilon E bar there. So you can write it in terms of D bar also. Okay, and they're asking the unit for energy density. It is joule per meter cube. Okay, समजलंय का सगळ्यांना? Yes or no? समजलंय का? Yes, anyone in class? Akanksha, Aishwarya. Okay. So today I'll upload the notes. You can refer this. Now the last point of this chapter is uniqueness theorem. Okay. So uniqueness theorem means here we are checking whether we are getting a single solution or not here. Okay. Means a unique solution we are getting or not. We are checking here. So this uniqueness theorem is frequently asked in examination. So whenever they are asking the question on the third chapter, they are asking this uniqueness theorem, boundary conditions, and capacitance. These are important. Okay, important points. So you can just go through these and practice for the problems. So there is no any question means numerical on this uniqueness theorem, but they will ask you the derivation only. So concentrate because the derivation is lengthy again. Okay. So here uniqueness theorem. So here all of you know the Laplace's equations. We have seen the Poisson's equations and Laplace's equations. So can anyone remember what is the Laplace's equation? What is Poisson's equations? Yes. What is Poisson's equation? Yes, anyone? What is Poisson's equation? At start of this chapter only we have seen. Yes. If anyone remember, if anyone noted. What is Poisson's equation? Hmm? What is Laplace's equation? What you are writing in your notebook? Are you taking any notes or not? So, okay. So in Poisson's equation, there is a rho, that is del square V is equal to rho divided by epsilon. Okay. And this for Laplace's equation, it is del square V is equal to 0, right? We have seen these equations also. We have seen how this is applied in all coordinate system. Okay, we have seen all the formulae for that. Okay, so here assume that the Laplace's equation has two solutions. Okay, say V1 and V2. Okay, what we are considering this Laplace's equation, that is del square V is equal to 0. So it is having two solutions, that is del square V1 and V2, and both are function of the coordinates of the system used, and these solutions must satisfy the Laplace's equation, right? So Laplace's equation is del square V is equal to 1, V is equal to 0, right? So we are writing for both that is V1 and V2. Therefore, del square V1 is equal to 0 and del square V2 is equal to 0. So both the solutions must satisfy the boundary conditions as well. Okay, means we have to consider the boundary. Okay, now at boundary, what happening we have to first check there. So we are considering the different fields there, means electric field intensity we are considering the electric flux density, right? We are considering their means one closed loop, one cylinder, and at boundary means when these are coming, so what are their directions, what are their quantities, we have seen in the all in the boundary conditions only, right? So uh, where at the boundary, this condition should be satisfied. So at the boundary, the potentials at different points are same due to equipotential surface. So if you consider any boundary, if you consider the any boundary, is for example, if you consider a sphere also, so inner part is different, the outer one is different, means the two mediums are different there. So you can consider any boundary. You can consider any boundary. So at the boundary, the potential is means it is a equipotential point. Means the potential is same, or uh, we can say that boundary is taken as a reference there. Okay, so at the boundary, the potentials at different points are same due to equipotential surface, means their potential is same. Now let the difference between two potentials is Vd. We are considering the two voltages, that is V1 and V2, and this potential difference is V2 minus V1, and it is denoted as Vd. So Vd is equal to V2 minus V1, and at boundary V1 is equal to V2. At boundary V1 is equal to V2 and the difference is V2 minus V1. Now using Laplace's equation for the difference Vd, this del square Vd is equal to, okay, so we have to use the Laplace's equation for this difference. Now del square Vd, Laplace's equation is del square V is equal to 0. Okay, Laplace's equation is del square V is equal to 0. So by using this equation, okay, So by applying this for Vd is equal to V2 minus V1. So we can write the Laplace's equation as del square Vd. Okay, del square Vd is equal to del square into bracket V2 minus V1, and it is equal to 0. It is equal to 0. Therefore, this del square V2, right hand side, just consider. So it is del square V2 minus del square V1 is equal to 0. Now, on the boundary, this potential difference is equal to 0 because this V1 is equal to V2, right? If this V1 is equal to V2, means potential difference Vd is equal to 0 on the boundary. Now, the divergence theorem states that, here all of you know the divergence theorem we have seen. Uh, uh, Instead of that a bar, we use their vector d bar, right? So you can use any vector, any vector. So the divergence theorem states that the volume integral of this del dot a bar into dv is equal to the closed surface integral of that vector field, that is a bar, over the surface. Okay, so it is equal to closed surface integral of a bar dot ds bar. Means the same vector is taken to the right side here. So here it is del dot a bar, means it is the divergence. Okay, it is the divergence, and this is that vector into ds bar. Okay, so this is your divergence theorem. So let this a bar is equal to vd into del vd. So we are considering this vector a bar as, we are considering this vector a bar as vd into del vd. Okay, and from vector algebra, this del dot alpha into b bar is equal to, we are considering the vector identity here. We have seen one vector identity in energy density in electric fields also. And there we first find the energy stored and then energy density, right? So in that equation also we have seen one vector identity. Okay, so likewise, this is also one vector identity. So it is del dot alpha into b bar is equal to alpha into del dot b bar plus b bar dot del into alpha. Okay, so this we have to use here. Here a bar is nothing but here vector b bar. Okay, means instead of this b bar, we have to put here a bar as vd into del vd. Okay, so we'll see that uh, this del into vd we have to put, and vd we have to put as a alpha here. So now use this for del dot vd into del vd into del vd with now this del dot, we have to find del dot a bar, right, which is left hand side for the divergence theorem. So uh, del dot vd into del vd, okay, means it is del dot a bar. Okay, just see here, we have to find this side del dot a bar. So a bar is vd into del vd, so it is del dot vd into del vd with alpha is equal to vd. This alpha we have to consider, and this del dot vd we have to consider as b bar. Okay, so if you write this in this equation, so it is del, concentrate here, del dot alpha, alpha is vd into b bar, b bar is del into vd is equal to alpha, means vd into bracket del dot b bar. Okay, so del dot b bar is del into vd plus this b bar is del into vd dot del into alpha, means del into alpha is vd. Okay, So we get this equation, and we know that del dot del is equal to del square. So here, instead of this del dot del, we can write as del square. So our equation becomes this as del dot Vd into del Vd is equal to Vd into del square Vd plus del into Vd dot this del into Vd. Okay, but what is the Laplace's equation? According to Laplace's equation, this potential difference is 0, but del square V is equal to 0. Okay, del square V is equal to 0 for Laplace's equation. Okay, so to satisfy Laplace's equation, we are making this term as 0. Means this term, this term becomes 0 here. That is del square Vd becomes 0. So del dot Vd into del Vd is equal to del dot Vd into del Vd is equal to del Vd dot this del Vd. Okay, del Vd dot del Vd. Now we know that this A bar is equal to Vd into del Vd, right? A bar is equal to Vd into del. Hello. So here A bar is equal to Vd into del Vd, right? So here we have to put here this equation. Now del dot Vd into del Vd is equal to del dot A bar, and it is equal to del into Vd dot del into Vd. Okay. So here simply we are considering this vector A bar as Vd into del Vd, which we have already seen, and we are just checking here uh, and equalizing this with this del dot A bar. Okay. Now the volume integral, according to the divergence theorem, we have seen the first integral is the volume integral. So the divergence theorem is volume integral of del dot A bar into dv is equal to the closed surface integral of A bar dot ds bar. Okay. So the volume integral of del into Vd dot this Vd, okay, dot del into Vd into dv is equal to the closed surface integral of that vector, that is A bar, and A bar is equal to Vd into del Vd dot ds bar. Okay, dot ds bar. Now, but at boundary, this Vd is equal to 0. Okay, because V1 is equal to V2 means at boundary that potential difference Vd is equal to 0. Hence, this RHS becomes 0 because the potential difference Vd is equal to 0 at the boundary only. So, this equation becomes the volume integral of this del into Vd dot del into Vd into dv is equal to 0. Is equal to 0. Now this is volume integral, and uh, to be evaluated on the volume enclosed by the boundary, right? So we know that when we are taking the dot product of any two vectors. So the dot product of any two vectors, that is c bar dot c bar, is equal to mod of c square. Okay, mod of c square. Therefore, volume integral of this del means instead of this c bar dot c bar, so what is this? This is also del into Vd dot del into Vd, and we know that this del is a vector quantity, right? Means this is a dot product of two vectors. Okay, this is dot product of two vectors. Therefore, the volume integral of this one, okay, that is del dot Vd square into dV is equal to 0. Is equal to 0 because this del dot Vd is a vector. Okay, it is a vector quantity. Now, this integration can be 0 under two conditions. Okay, so when this integration can be 0, so when the quantity under integral sign is 0, means this del into Vd square should be 0. Okay, ते तरी 0 पाहिजे किंवा the quantity is positive in some regions and negative in some regions by equal amount, hence 0. Okay, किंवा that quantity in some region it should be positive and in some region it should be negative, then the total amount will become 0. Okay, then only this term can be 0. Okay, so but here the square term cannot be negative in any region. Okay, square term cannot be negative in any region, and hence the quantity under integral must be 0, means the mod of this del into Vd square should be 0 there. Okay, means this del into Vd is equal to 0. So here, as the gradient of Vd, that is the difference Vd is equal to V2 minus V1 is 0, means V2 minus V1 is constant and not changing with any coordinates. But considering boundary, it can be proved that this V2 is equal to V1 is equal to constant. Means we are taking that at boundary, these both are same, means V1 is equal to V2, and this proves that both the solutions are equal and cannot be different. Means by considering this also, we can say that this V1 is equal to V2, or this del square V is equal to 0. So this is your uniqueness theorem. So this is asked in examination many times. So everyone concentrate for this, and in this way our third chapter is over now. Okay, third chapter is now over. So only half section is covered. Still our one section is remaining. So it will require some less lectures than the first section. Okay, so in this third chapter, we have seen, we'll revise some points. In this chapter, we have seen first conductors and dielectrics. Chapter name, conductor and dielectrics. We have seen current and current density. So here the definition of current, current density, then relation between I and J. Okay, so I is the current and current density relationship we have seen. Current I is equal to the surface integral of J bar dot ds bar. Now from that they are asking the examples. Remember, so we have seen the example also. Then the point form of Ohm's law. So this is also asked in examination, point form of Ohm's law. Then these terms sometimes asked, that is drifting of electrons, drift velocity, drift current. You should know these terms. As the MCQ also, they can ask you these terms, the definitions. Okay. Or they may give you the definition and they will ask you the term. What is mean by this? Okay. Then continuity equation of current. This is also important. Continuity equation and uniqueness theorem. Okay. Out of these two, either one can be asked, either continuity or uniqueness. Okay, they are asking. So this is also somewhat lengthy derivation. Then we have seen some examples on this also. Then Poisson's and Laplace's equations. Okay. So for Poisson's, remember, this del square V is equal to minus rho V divided by epsilon. And for Laplace's, this del square V is equal to 0. Remember, this equation is also asked for 4 marks. Okay. Remember all equations. Then we have seen when we are using this del square operator, we have seen del operator in previous chapter, but here it is del square operator, means we have to perform this operation 2 times. Okay, means derive any equation 2 times there. Okay, take derivative 2 times. Okay, then this is example. Then we have seen the dielectric materials. Then properties of dielectric materials, polarization, what is mean by polarization. Okay, then mathematical expression for this. Okay, so here you will require the concept of this dipole moment, that is P bar is equal to Q into D bar. From that also there are some examples. Then boundary conditions, these are very important. In examination, there is a compulsory question on boundary conditions, because in second section also there are boundary conditions, right? These are for magnetic fields and these boundary conditions are for electric field. At least one question is there from magnetic or from electric. They may ask you either example or derivation. काहीतरी हे 100% असणार आहे. मग दोन्ही साईडचं करताना तुम्हाला काय करायचंय, दोन्ही कंपॅरेटिव्हली स्टडी करायचं. ओके, म्हणजे इथे पण बाउंड्री कंडिशन्स आहेत, मॅग्नेटिक फील्ड मध्ये पण बाउंड्री कंडिशन्स आहेत. मग इथे कोणत्या क्वांटिटीज आहेत? Electric field intensity, there is magnetic field intensity. Here electric flux density, there is magnetic flux density, right? So likewise you have to compare the terms and remember the equations. Now here the tangential component of electric field intensity is same, and the normal component of electric flux density is related with the epsilon r, that is relative permittivity. Here you have to remember. Okay, so here you can check at first. Okay, this tangential component is same, and the of electric field intensity and electric flux density is related with epsilon. Okay, tangential component. And when you are considering the normal component of electric flux density is same, dn1 is equal to dn2. But if you take the normal component of electric field intensity, then it is related with the epsilon r. Okay, so in this way you have to remember there. Then refraction we have seen, and example also we have seen. Then next point we have seen is the capacitance, concept of capacitance. So this concept is very important because in GATE examination, this electromagnetic engineering is asked for 4 to 6 marks. Okay, and out of that 4 to 6 marks, one compulsory question is there on capacitance. Okay, that question can be of 1 mark or 2 marks, but mostly the questions on capacitance are of 2 marks. Okay, so you should know this formulae, you should know the concept of capacitance. Okay, because if you have studied basic electronics, in that also this concept of capacitance is covered. Therefore, and this is easy as compared to other derivations, right? So you concentrate those who are interested in gate examination. This point is important. So remember all, and everywhere the uh, units are important. Okay, units are also important. So in examples also, while solving examples also, you just check there that what is asked in examination, right? And what can be the unit. Okay, so from formally, if you don't remember any unit, if you know the formula, from that also you can write the unit, right? So you know that how to write the unit. Then we have seen the parallel plate capacitor. So this derivation they may ask you example. So remember all the formulae here, basic relations you should know. For example, this epsilon is equal to epsilon 0 epsilon r, then d bar is equal to epsilon e bar. Like such relations, these formulae you should remember. You should know these basic formulae. Then you can go for the C, then you can go for E, for CF like formulae, right? But before that, you should know the basic concepts first. Okay. Then what is this epsilon 0? Means many times actually the constants are already defined in question paper also, but many times they are not giving. Then that time you should know what is the constant epsilon 0, that is 8.854 into 10 raised to minus 12. So you should remember these constants also. Okay. Then we have seen the spherical capacitor. Okay, and after spherical, the example, uh, from spherical also they may ask you example. So any imaginary data can be given. Then we have seen the energy stored, energy density, and last uniqueness theorem we have seen. So our third chapter, means the first section, is over now. So if there is any doubt, you can ask me. Any doubt is there? Is there any doubt, Preeti? Yes, Nehal. Yes, anyone? Is there any doubt? आहात का लेक्चर मध्ये? समजतंय का मी? का काहीच समजत नाहीये? का सगळंच समजले? Yes. In which stage you are? Yes, Swapnali. In which stage you are? You are getting everything or nothing? Okay. So I think no one has any doubt. Everything is clear to you, right? I consider this as, and we conclude here the third chapter. Okay. In next lecture, we'll start our fourth chapter, that is static magnetic fields. Okay. That chapter is also important. The first two chapters from first section and fourth and fifth chapter, or fourth and sixth chapter from the second section you can do. If you means if the exam is theory, means offline, then you can prepare for these chapters. At least it is for the passing. Okay. But for online, you have to prepare everything and any question can be asked. So for today, we'll stop here. And yesterday only I told you that the tutorials are uploaded on Drive. Everybody solve that tutorial. I'll upload these notes also today, the third chapter notes. So you can solve up to the third tutorial. Okay, everybody solve the tutorials there. Okay. And after that, I'll provide you one Google form. Okay, and on that, everyone upload the solve tutorials. Okay, because these are important for the while giving the ICMS, because we are considering this tutorial marks also. Your attendance and your ICM, your tutorials. Okay, that will be considered for the ICMS. So thank you all and have a nice day. I'm ending lecture now. Thank you.